we solve questions about reactions? Let's take the reaction of hydrogen with oxygen to form water as our first example. The first thing that's important to do is to determine what the balanced equation is for the reaction. So for the formation of water, it's 2H2 plus 1O2. We normally don't write that 1, just O2, gives 2H2O. What is the meaning of that? For every 2 molecules of hydrogen gas, remember hydrogen gas is H2, not H. And here we have 2 molecules, 2 molecules of hydrogen gas. So for every 2 molecules of hydrogen gas, you need 1 molecule of oxygen gas. Now, during the reaction, the atoms of these reactant molecules break apart, separate from one another, and then during the reaction, they rearrange. You can say that oxygen ends up there with that hydrogen and that hydrogen, and that oxygen ends up there with that hydrogen atom and that hydrogen atom. So for every 2 molecules of hydrogen that react, you need 1 molecule of oxygen, and that will form 2 molecules of water. That's the product. Now, of course, when you actually make water by this reaction, you are not going to only react 2 molecules of hydrogen and 1 molecule of oxygen. That is so little. There's no way you are going to get that right to react that little. This is a ratio, meaning that if you have 2 million rather than 2 hydrogen molecules, you will need 1 million oxygen molecules, and you will form 2 million water molecules. That's also just an example. There are infinite number of possibilities, but they are all in this ratio. 2 for every 1 for every 2. And if you understand that, then solving problems about reactions will be quite easy. Let's see how. So the first step is to write this ratio that I've just been speaking about in different forms. We're going to write a mole reacting ratio, a molecule reacting ratio, a mass reacting ratio, and a volume reacting ratio. And then we will get to some questions where we apply these ratios. The mole reacting ratio we've already spoken about. 2 moles of hydrogen for every 1 mole of oxygen to form 2 moles of water. Very simple. This simply uses the coefficients in the balanced equation. Those coefficients give us a mole reacting ratio. Now, the mole reacting ratio is also a molecule reacting ratio. I'm going to show you why the long way round, and then I'll show you how simple it actually is. So we can ask ourselves, 2 moles, how many molecules is that? Well, it's 2 groups of this number, which is a mole. 2 moles of molecules is 2 times 6,02 times 10 to the power 23 molecules. 1 mole is 1 group of a mole, 6,02 times 10 to the power 23, and 2 moles is 2 groups of that number. Now, can you see that we could simplify this to be 2 is to 1 is to 2, because we could divide through everything by Avogadro's number, 6,02 times 10 to the power 23, and we're left with 2 is to 1 is to 2. So that's why a molecule reacting ratio is the same ratio as a mole reacting ratio. That's not the same as saying moles are the same thing as molecules. No, moles and molecules are very different. But if you have the reacting ratio in moles, that is also the reacting ratio in molecules. But it's not the same reacting ratio as a mass reacting ratio. So moles and molecule ratio are the same thing, but that doesn't mean 2 grams of hydrogen reacts with 1 gram of oxygen to form 2 grams of water. No, no, no. A mass reacting ratio is quite a different thing to a particle. These are particles, and they have the same reacting ratios as one another. But mass reacting ratio is quite different. So we need to ask ourselves, 2 moles of hydrogen gas, how many grams is that? And we look at the periodic table, and we see that the molar mass of H, not H2H, is 1. So that's 1 gram per mole of H. And we have 2 H atoms per molecule, so we must multiply that by 2. And we are finding out what the mass of 2 moles of such a substance is. So we must multiply it by 2. So 2 moles of H2 have a mass of 4 grams. 1 mole of O2, what's the mass? So each mole of O atoms has a mass of 16 grams, and there are 2 moles of O atoms in every 1 mole of O2 molecules, and we want to know the mass of 1 mole of O2. So that is 2 times 16, 32 grams. 1 mole of O2 has a mass of 32 grams. Here we're asking ourselves, 2 moles of H2O, how many grams? Each mole of water has a mass of 18 grams. 16 for the O, 2 times 1 for the 2 H's. So 18 grams is the molar mass of H2O. And here we are asking, what is the mass of 2 moles of that? So it is 36 grams. Notice that over here on the reactant side, we have 4 grams plus 32 grams. That makes 36 grams. And here we have 36 grams. Because matter cannot be created or destroyed. Mass does not disappear, nor does it appear from nowhere. So these are the reactants. And if we had 2 moles hydrogen reacting with 1 mole oxygen, we would need 36 grams of reactants. And this is the product, and we would get 36 grams of product. No matter disappeared, no matter came from nowhere. That's good. Law of conservation of matter. Okay, so here we have a mass reacting ratio. Now let's have a volume reacting ratio. So we ask ourselves, 2 moles of hydrogen gas, what volume will it occupy? We are saying at STP. We cannot say for any other temperature and pressure without using the gas equations. But for STP, 2 moles of hydrogen gas would occupy 2 times 22,4 decimeters cubed, which is 44,8 decimeters cubed. And 1 mole of oxygen gas at STP would occupy 1 times 22,4 decimeter cubed. And 2 moles of water vapor at STP would occupy 2 times 22,4. Now here again, notice we could divide through by 22,4. And then you can see that the volume, molecule, and mole ratios are the same. 2:1:2. And this is actually a good idea because if you do that, you can actually apply this to any temperature and pressure, not only STP. So that's a very useful thing to remember. So particle and volume ratios are the same as one another. Mass ratio, though, is totally different. Now, the important thing to realize here is that all of these values here are equivalent amounts for this particular reaction. They won't be equivalent necessarily for another reaction, but we are answering questions about this reaction. And for this reaction, all the values here are equivalent to one another. And so that means that we can create conversion factors from any pair of these values. Which pair will be useful will be determined by what unit we are given and what unit we are required. Let's get some practice with that. How many moles of oxygen gas? Whenever we are told oxygen gas, we immediately write O2, never O, because oxygen exists in the elemental form as a gas in the atmosphere as O2, never O, are needed to fully react with 5 moles of hydrogen gas. Same thing. As soon as you hear hydrogen gas, you know we're speaking H2, not H. So now we need a conversion factor with equivalent amounts at the top and the bottom. Over here in the table, we have many equivalent amounts, and any pair of them can be used as our conversion factor. But not any pair would be useful. Only the pair that has moles of hydrogen at the bottom to cancel away the given unit, and moles of oxygen molecules at the top to introduce the required unit. Only that pair will be useful. Now you can't stop there because we haven't said how many moles oxygen is to how many moles hydrogen. We still need to do that part. So we look here at the table and we see 2 mole hydrogen reacts with every 1 mole oxygen. So for this particular equation, these values are equivalent. They're not always equivalent. It's just for this reaction because that's the ratio in which they react. Very easy. 5 divided by 2, 2.5, 2,5 moles of oxygen. How many molecules of water will be produced when 2,9 moles of oxygen react fully to form water when they react with hydrogen? So again, we need a conversion factor, which we're going to take from this table, making sure that our conversion factor is useful. In other words, mole oxygen needs to be at the bottom, and not mole, but water. Water molecules. We could write it out in full if we wanted, but if we write H2O, it's obvious that is molecules at the top. So what is our conversion factor that's useful? Here we have water molecules, and here we have moles of oxygen. 2 moles, which is 2 times 6,02 times 10 to the power 23, of water are formed every time 1 mole of oxygen reacts. 2.9 times 2 times 6.02 times 10 to the power 23, 3,49 times 10 to the power 24 water molecules. What mass of hydrogen? In other words, how many grams of hydrogen? That G there doesn't mean gas. That G there is gas. But here in the question, how many G is how many grams hydrogen? You can go and add gas if you wish, but it's not really necessary. How many grams of hydrogen is needed to react with 15 grams of oxygen to form water according to the equation? So we need our conversion factor, which refers to this particular equation, and we must make sure that grams of oxygen are at the bottom to cancel away the given unit. Grams of hydrogen are at the top to introduce the required unit. Do you see that we're going to use the mass reacting ratio for hydrogen to oxygen? 4 grams of hydrogen for every 32 grams of oxygen. So every time 4 grams of hydrogen reacts, you need 32 grams of oxygen. So if instead of 32 grams you actually have 15 grams, then how many grams of hydrogen do you need? 15 times 4 divided by 32. 1,88 grams of hydrogen. What mass of hydrogen, again, how many grams of hydrogen, is needed to form 50 decimeters cubed of water at STP? So since it's at STP, we can use these values given here, 22,4 decimeter cubed for every mole. And we need to multiply this by a conversion factor, which we get from this table up here. See if you can give the conversion factor before I show it. Our conversion factor needs decimeters cubed of water at the bottom to cancel away the given unit, and grams of hydrogen at the top to introduce the question unit, the required unit. So we need a mass volume ratio of how many grams of hydrogen react every time to produce how many decimeter cubed of water at STP. Notice that's a ratio. That's not how much is actually reacting now in this situation, the actual amount for this situation. That's what we're required to find out. So we use the ratio, we apply the ratio to this particular situation to find out how much hydrogen we need in this particular situation. But it will still be in the same ratio as given in this block, because they always react in this particular ratio. You just need the ratio in a useful format to apply to the question. 4 grams of hydrogen react every time 2 times 22,4 decimeters cubed of water are formed. So in this particular case, where you don't have 2 times 22,4 decimeter cubed water produced, but rather 50 decimeter cubed water produced, then how many grams of hydrogen do we actually need? 50 times 4 divided by, we can say divide by 44,8, or we can go 2 steps on our calculator, divide by 2, divide by 22.4 equals 4,46 grams of hydrogen. How many moles of oxygen gas are needed to form 30 decimeters cubed of water at STP? Since it's STP, we can use these values, these 22,4 decimeter cubed per mole values. So we need to multiply this by a conversion factor, which refers to the reacting ratio for this particular particular reaction, but we must choose a useful reacting ratio. We can give the reacting ratio in many forms. Which is the useful one? Try yourself before I show you. We need decimeter cubed of water at the bottom. We need mole of oxygen at the top. So this is a particle volume reacting ratio. So we know that 1 mole of O2 produces 2 times 22,4 decimeter cubed of water. That is the ratio. We apply that ratio by multiplying with a conversion factor to this particular situation where we have 30 decimeter cubed of water, and we want to know how many moles of oxygen then do we need. 30 divided by 2 divided by 22.4, 0,67 moles of oxygen.